So in this video, we're going to go through and analyze this equilibrium shown between the cobalt water complex shown here plus chloride going to the cobalt chloride compound plus water. And one of the neat things about this equilibrium is the two cobalt complexes are colored. So this cobalt water complex is a very pretty red, or it's really a pink color, and this cobalt chloride is a very pretty blue color. So we can actually visually see where this equilibrium lies based on the color of the solution. And when we look at this, we're going to dissolve our cobalt complex in isopropyl alcohol. So the first thing we want to do when we think about this is let's go ahead and write an equilibrium constant expression for this. And I went ahead and did this, and it's shown below. We're going to again put products over reactants. And one of the things to take note of when we did this is we have products, cobalt chloride, times water to the 6th power. And the reason we're including water in this equilibrium is because we're dissolving an isopropyl alcohol. So we're not an aqueous solution, so water is not a pure liquid in this case. So we're going to include it in our equilibrium constant expression. And then on the bottom, we'd have our reactants, so our cobalt water complex times our chloride ion concentration to the 4th, because there's a coefficient of 4. So when we think about this, we can ask ourselves, how can we force the equilibrium to the reactant side? All right, so this is, if we want our cobalt complex to be over here on the cobalt water complex, and we want our solution to be pink, how could we do that? This is an application of Le Chatelier's principle. And so in order to do this, we'd have to add our products. And so in this case, if we add water, which is a product, it's going to force the reaction to the left. And if we added chloride, we'd force the reaction to the right. So we can think about that application of Le Chatelier's. If we want to be on this side, we would just add more water to our solution. And if you want to be on the product side, you'd remove water or add chloride to it. And the next thing we're going to think about is what happens to this equilibrium if we add or remove heat. And what we're really getting at is this reaction endothermic or exothermic? And so we can think about that. And to start off, we'll show a video and look at this reaction and what happens. And so before I play this video, again, think about this equilibrium. So this cobalt water complex is pink, the cobalt chloride on the product is blue. So here's our bottle of our cobalt that we start with. We start off with a very pretty pink compound. So we're actually starting with this cobalt water complex over here. The first thing you'll see me do is add some isopropyl alcohol. So that's from this bottle here to dissolve this up. And so we'll go ahead and hit play. We're going to add the isopropanol, and then immediately you can see once we add that isopropanol, we can see we are mostly on the product side of this reaction, and we know that because of the color. This is a blue complex. We clearly see this is blue, and so we are mostly on the product side. So what's happening now is I took some of that and I just put it in a test tube. And what we're going to do is add a little deionized water. And so we're going to go ahead and add the deionized water. And just before we do it, let's just recall what we said. We're on the product side. If we add water, water is a product, we should see a shift to the reactant side. So we should see a color change from blue to pink. So let's go ahead and watch. We're going to add some drops of water. And as I add the water, especially if you watch the bottom of the flask, you can start to see this color change happening, right? We see the blue color going away. We see pink color forming. And I'm going to go ahead and mix this on our vortex. Put some white in the background. And you can see very quickly we have a color change from blue to pink as we shift that equilibrium to the left toward our reactant side. All right. What we're going to do now is we're going to ask what happens if we add heat. And so over here, I have a warm water bath. So this is just a beaker of water. It's on a hot plate. So this is hot water. And then over here, we have a ice bath. So we're going to take our equilibrium, which is now shifted towards the reactant side. We're going to put it in our warm water and say, what happens? So we'll go ahead and watch. So here we go. Here's our pink colored, so we're mostly on the reactant side. We put this into warm water, and then we can sit back and watch and say, what is happening to the color of our solution? This is my camera work, and so what's going on? And so what I hope you are observing is the formation of that blue color returning. And so when we added heat, what happened? We shifted this reaction to the product side. We converted to the cobalt chloride. If we take that same test tube out and put it now in our ice water bath, we can ask ourselves, what's going to happen? So now we're removing heat, right? We're putting this in cold water, so we're going to take heat away. And so we can watch this for a second and ask, what is going to happen? Here, I'll rotate the beaker so you can see it a little bit better. And we should see, notice the blue color is disappearing. We are now going back to a pink color. So by removing heat, we are shifting this equilibrium back to the reactant side. So by adding or removing heat, we can actually force this equilibrium to one side or the other. Right? So what happened if heat is added or removed? And what we said, if we add heat, it forces to the product side. So now we have to think about, is this reaction an endothermic or an exothermic reaction? Right? So we started off, if the reaction's cold, we have mostly reactants, right? It's a pink colored solution. If we're at room temperature, we're sort of in this in-between stage. There's definitely some of this pink compound, definitely some of this blue compound. When we're a hot solution, we have a very intense, bright, pretty blue color here. And so the addition of heat is forcing us to the product side. So thinking about Le Chatelier's, if we add heat, we are forcing it to the product side. That is telling us that heat must be a reactant. And if heat is a reactant in a reaction, we think of that as being endothermic. So this reaction requires heat to go to the product side. So heat's a reactant. This is an endothermic reaction. And that's also why when we removed heat by putting this in an ice bath, you remove a reactant, we're pulling the reaction back to the left to go back to form our reactants. So I hope that's helped us visualize and understand Le Chatelier's principle as it applies to endothermic and exothermic reactions. Thank you.